So in dealing with trigonometry, we often have to know how the trig functions relate to each other, what some of the common values are, and what their behavior is as functions. So I wanted to review the basics. There's two ways of defining the trig functions. The first one I want to look at is defining it on a right triangle. So if we take a right triangle and we label one of the other angles theta, then we refer to these sides as the side adjacent to that angle, the leg here opposite, and then the one across from the 90 we call the hypotenuse. And then really the trig functions are just ratios of the sides of that triangle. So sine is the opposite side over the hypotenuse. Cosine is the adjacent over the hypotenuse. The tangent is sine over cosine, or opposite over adjacent. And then from there, the other three are just the reciprocals of these. So cosecant of theta is 1 over sine. So it's the reciprocal. Secant is 1 over cosine, so the reciprocal there. And lastly, cotangent is the reciprocal of tangent. A word on terminology here. The reason we have these co-names is that they are the corresponding function if you were looking at the complementary angle. Notice, for a right triangle, these two angles are complements. They add up to 90 degrees. So for example, if I put another angle here, I'll call it beta. Sine of beta, this would now be the opposite for beta, and this would be its adjacent. So sine of beta would be this side here over the hypotenuse, but that's cosine of theta. So the co-function for b corresponds to the other function for theta because they're complements. So each one of these functions, sine has a cosine, tangent has a cotangent, secant has a cosecant. That naming is because that's the corresponding function for the other angle in the triangle. Hence the name co for complement. Another thing to notice is that because we're defining this on a right triangle, theta is strictly between 0 and pi over 2. It can't be 0 or else the triangle disappears. There's no triangle anymore if the hypotenuse collapses down. And if you move that hypotenuse up to a right, then you've got field goal. You've got no triangle again. So this is a limited case and doesn't get into all the interesting things of trig functions, of their periodicity and the ability to revolve round and round. Those we need another definition. Now, I do want to talk about, in general, it could be hard to compute these things. If I just give you an angle, sine of pi over 14, how do you figure out what these things are? Well, there are some angles that we can figure out just from geometry. So I want to cover those real quick so we know where these values are coming from. The simplest is pi over 4 because these two have to add up to 90 degrees, or pi over 2, when one of those angles is pi over 4, they're both pi over 4. And that makes this an isosceles triangle, which means we know from geometry for an isosceles triangle, those two sides are the same. Well, from Pythagoras then, that squared plus that squared is the hypotenuse. So the hypotenuse then has to be square root of 2a. because I can make that relationship, now I can actually talk about what is sine of pi over 4. Well, pick either angle, doesn't matter. Sine is opposite over hypotenuse. So a over root 2a, but that's just 1 over root 2. What is cosine of pi over 4? Well, cosine's adjacent, but the adjacent and the opposite are the same. So it's also 1 over root 2. Now you'll often see this rationalized as root 2 over 2, but either way, same thing. So we can get sine and cosine for pi over 4, which means we can get all of these, because once you know these, we know all the sides of that triangle, we can do all these ratios. But let's just look at sine and cosine for now. The other triangle that works out quite nicely is if you were to start with an equilateral. So if it's equilateral, all these sides are a. That also means all these angles are the same, but they have to add up to pi, or 180. So that means each one of these angles is pi over 3. I'm not going to label that one because I'm about to cut this triangle in half. So because it's equilateral and equiangular, if I cut it down the middle, I get mirror images of each other. So that means this side now is 1/2 a. We've got a right triangle. I cut this in half, so this little angle here is pi over 6. I've kind of created 2 mirror images there. So let's just focus on 1/2 of this. I've just created a triangle. I know this side, I know this side, I know the angles. I just need that height. Well, that height by Pythagoras, 1/2 a squared plus our height squared should equal the hypotenuse squared. So if I move, this is 1/4 a squared, subtract it, I get 3/4 a squared, square root 3 over 2a. So I know my height's root 3 over 2 times a. Now I can do the same thing. Now I know all the sides on this little triangle here. So we can say what sine is of either angle. We're getting 2 for 1 on this one, pi over 3 and pi over 6. Let's start with pi over 6. Opposite over hypotenuse. So sine is 1/2. But because pi over 3 is its cofunction, that means that must be cosine for pi over 3. Or just go back to the triangle. What's cosine adjacent over hypotenuse would also be 1/2. And then we just need the reverse. So what is sine of pi over 3? Well, here's pi over 3. Sine would be opposite, square root of 3 over 2a over a. So just square root of 3 over 2. And then cosine of pi over 6 would have to be the same, because these are complementary functions. You can get all that off of that triangle. So these are the values here, pi over 4, pi over 3, and pi over 6, where we can actually get those things exactly. Once you start talking about angles in between there, any random angle, it's not trivial at all how you could get that. And actually, that's a big part of what we talk about when we get to series, is we will look at how can we express these trig functions in a way that would allow us to do computation. Right now, we're just getting lucky with some facts about geometry. But what if you just want sine of some arbitrary angle? What do you do?